Hi everyone, so we are here with a new problem, and the today problem is critical connection in a network. So it is a hard type of problem, and I also feel the same because we can solve it with a brute force, but in that approach we have a time limit exceed, and but there is a new algorithm. I think all of us learned today that new algorithm, and that is the main thing why it is hard. So before solving it, let's understand what is the problem. So in that problem, basically, we have n servers, which is ranging from 0 to n minus 1, connected by a unidirectional server to server connection, forming a network. Connections at AIBI represents a connection between the two servers. Now what we have to do, we actually have to find a critical connection such that if I am able to find a critical connection, I can disconnect servers. Okay, so let's take an example in order to understand it more clearly. So now in this example you can see that these are all the servers, which is 0, 1, 2, and 3. In that case n equal to 4, and all the servers are connected to each other. Now what we have to do, basically we have to find a connection between two servers such that we will disconnect one server from this whole bunch of servers. What I mean by this, let's understand this. So let's suppose if I remove this edge, so now you can see this 0 is connected to 1, and also by 1 it is again connected with 2. So by removing this edge, it is not affecting any connection between these nodes. That's why it is not a critical connection. If we remove this, then we are not able to, okay, and if we remove this node, then 1 2 connection is removed, but 2 is again connected with 1 with the help of 0 node. And similarly, if we remove this one, 1 and 0, we are able to connect with 1 with the help of this 2 node, right? And now if we remove this, so now you can see 1 is connected with 3, and if we remove this edge, there is no other way we are again connected with this 3. So that is a critical edge. That is a critical edge. Okay, from this problem it is understood that it is a graph type of problem, and to understand this, generalize this, how we can understand this. So you can take each node as a component. Okay, so I can take each node as a component. So let's suppose this is one node, this is one node, this is one node, and this is one node, right? Now this is one component, right? And what is happening, all these component, when we connect this, now this 0 3 is a one component, 1 is a different component, 2 is a different component. If we connect 1 and 2, so this is one component, this is second component, and if we connect this, so this whole is a one component. So what we want to do is, this is one component, okay, and we want to find some edge such that if we remove that edge, we are able to break this component into two other components. Let's suppose if I remove this edge, if I simply remove this edge, okay, let me remove it, you can see there are two components created, right? And that's why we can say this 0 2 is a critical component. Okay, let me add it again. But here we can take another example to understand it. Let's suppose if I add this one, right? So if I remove this, this is not a critical component because the component remains the same. If I remove this, this is not the critical component. And if I remove this, this is also not the critical component because the component remains the same, one component. But if I remove this, this is, we can say, a critical edge. That's how it will create two different components. This is one component and this is another component. Great. Now from this example we can understand one thing, that in these nodes there is a cycle. Okay, there is a cycle. What I mean by cycle, in graph, cycle means when there is the number of node is equal to the number of edges or more than that. In that case always cycle creates. Now you can see 1 2 3, there are three nodes and there are three edges, right? In that case always this cycle uh, are there. So when there is some cycle, we are not able to find any critical section, right? So basically we need to find such edge which not makes cycle. Okay, first understand this by some brute approach, some very brute approach, how we can basically solve it, right? And after this, we can think about a very new algorithm, about a very optimized algorithm, and that is an interesting one also. I hope you understand the problem, what is actually happening. Now let's see how we can solve it. So, taking this example, I will try to solve this. Okay, great. So now we have n equal to 4 and we have given edges. Okay, so we have a edges array, like this is the edges array. Let me take it, which is 0 1 1 2 2 0 1 3, right? So it is 0 1 1 2 2 0 1 3, right? These are all the edges we have, and we have to find the critical edge. So what I do, I will take this 0 1, this 0 1, remove it. Okay, and what I do, I will let's suppose start from this node and make a DFS, depth for search. What is depth for search? Basically we are doing recursion, and from each node, whatever the node which is connected with this, we are iterating it. Okay, so let's suppose we are at one node, so one node is encountered. Now from this 0 is connected to 2 because we remove this 0 1 connection. From 0 we go to 2. Okay, and there this is the second node. From this 2 we are able to go to 1 because it is connected with this is the third node, and from this one we are able to reach 3, which is the fourth node, right? So now we have total 4 nodes and we are able to iterate all these 4. So it means by removing this 0 1 node or 0 1 edge, we are also able to traverse through whole graph. So it is not a critical edge. Critical edge is when we are not able to iterate all the nodes. Great. So do the same process. Now let's remove 1 2. So if I remove this, let's start from this 0. So this 0 is connected with 1, so I will go to 1. This one is connected with 3, so I will able to go to 3. Now there is no edge which is connected with 3, so we are not able to go. We come back 1 and we come back 0, and from 0 we again go to 2, right? And in that way you can see we are able to iterate all those 4 edges, and this is not a critical edge, we can say. Okay, now let's take this 1 3. Now let's break this. Now from 0 we go to 1, and from 1 we go to 2, and from 2 we are again going to 0, which is already visited. So we come back from this, we come back from this, and 1 2 3 there is no such connection because we remove it, and we come here. Now in that case we are able to iterate 3 nodes, right? In that case we are not able to iterate all the nodes, and that's how we can say that 1 3 is a critical section, right? So this is one approach. Now in that approach, what we are doing, we are using DFS. And what is the time complexity of DFS? Time complexity is vertices and edges. So basically for each vertex we are also iterating the edges, and also in that case what we are doing, for each edge we are doing DFS, like we are removing some edge and then doing DFS, then we removing some edge and then doing DFS. So for all the edges we are doing this DFS. So it is E cross V plus E time complexity, which is too high, right? It's not a good way to solve this problem. So now what is the good way to solve this problem? Okay, now let's come to that point. So in order to solve this problem, there is a very popular algorithm to solve it, and the name of algorithm is Tarzan algorithm. Okay, let me write the name. So the name of algorithm is Tarzan algorithm. So what this algorithm said, let me show you. So basically, as I tell you, let's suppose I will take 0, then 1, then 2, then 3, and then it is like this. So this is one whole component. Okay, so this is one big whole component. Okay, now what we are doing at the end, we basically remove some edge and try to find whether we are able to iterate whole edges or not? Okay, can we uh, can we make it more optimized? So Tarzan algorithm say that, let's suppose from this node, we start. Okay, from this node we start. Let's suppose this is our source from where everything getting started. So we, from this, we reach to that, right? And from this node we are able to reach there, right? And from this we are able to reach there, and from this we are able to reach there again, which is already visited, right? Now what we do, we basically try to combine those nodes which are in some cycles, right? What I mean by this, now you can see that from 2 we are able to reach at 1, from 3 we are able to reach at 1, from 1 we are able to reach at 3 by 2, right? Or we can directly reach here, right? But to reach at 0, there is only one path, which is from 1 to 0. There is no other way present here with the help of which we can reach to this 0 node. And that is a differentiating thing. That is a new thing. We can use this and we can simply say that this 0 1 is the edge which is a critical edge. How the Tarzan algorithm works, let's try run once for you and then see how we are able to uh, apply it. Okay. So in this algorithm, there are two things. There are low and there are start. But I will show you a different way. So basically, what I do is low and ID, basically not start but ID. So what we do in this algorithm, let's suppose we are at this 0th node. Okay, so what we do, we said that this 0 node is discovered at this time, at this point. So this 0th node is, let's suppose uh, we capture it at 0th second, right? Now we go here and this one node is captured at 1 second. Now we go to this node because it is connected with this. So we find this second node at 2 second, and this 2 is connected with this 3. In that case, this 3 node is captured at 3rd second. Now this 3 is again connected with 1. But now you can see from this node we are trying to capture this one, but this one is already captured. In past we already captured this, right? And from this part, from this past or from this node we reach there, and now we are again see that node. It means we have some sort of cycle which make it happens that from some future node, 3 is a future node, we are able to reach some past node. And how we come to know that this is a future node and this is a past node? Due to its timer, in which time this node we find and in which time this node we find. You can see that this node, the current node we are at, it is captured at 3rd second, but it is connected to one which is captured at 1st second. So we can simply change its timer to 1, which tells us that this node is also connected with this thing. Now we come back from there because there is no other connected node with this, and we again check its timer. What we expect? We expect from the future node that it should be capture in the let's suppose this is captured in second. So for the future node, it is expected that it should capture in next hours, in next time, means it should be captured in 3, but it is captured in 1 second. It specifies that it is already related to some past node, and when the time of this node, like you can see it is captured in 2, and it says I am also captured in 1 second. then we change it to 1. Okay, and again you can see it is same, but now in that node you can see it is not connected with anything. That's why it is captured at 0 second and it is captured at 1 second. And that is the way we can say that this node is not connected by these cycles or by other nodes. That's why we are not able to convert the other, because if it is connected, let's suppose with this, then what we do, this one is again, like this is not one, this is now 0, and it tells it is connected with this. That's why we make its timer to be 0, but it is not connected with this. That's why we are not able to propagate this timer with other nodes, but this one is connected with this because there is a cycle which is already visited. That's why we are propagating its timer to all that nodes, and this similar timer tells us that all this node is one component, but this different timer which is 0 and 1 tells that these are two different nodes. Okay, and that's how this is a critical edge. If we remove that edge, we are able to make two components, which is 0, this one as one component and this whole as another component. Now how we basically solve it, we basically do the same and try to solve it. Okay, let me go to the code and we'll show you how we are able to solve it. So there are a visited there is a visited array which tells which node is visited and which node is not visited. There is a low, right, and there is a capture. So capture tells which node is captured at what point of time, and this low tells it actually gives a identity to each node. Okay, and this is the answer array that we have to return the critical section in it, and this is the graph. You know how we create it before, I will tell you. And this is the main algorithm, Tarzan algorithm. What we are doing here, initially we are at the 0th index and there is no parent node. We also have to capture the parent node. Why? Let's suppose from this 0, because it is undirected graph, right, we reach 1. Now 1 is also again connected to 0, but we don't have to go back again, otherwise we will in this loop, right? So we have to capture that when we reach 1, what is the parent node of 1, which is 0, and that's why we don't have to again go back to the parent node. Okay, so initially we are at the 0th node. Okay, and there is no parent node, that's why we are passing -1. Now this 0th node is visited, that's why we make it true, and it is captured. So we create a timer which is initially 0, and after assigning the value we will increment it. Got it? So we will say okay, this 0th node is captured at 0 second, and then we increment the timer 1 by 1. Now this 0th node, all those neighbors we will loop and we will check, right, because for this one 0 is also neighbor, but this 0 is a parent of 1. So if the current node is a parent, so if the neighbor is a parent of like parent node, we don't have to iterate, we simply have to continue. The other thing is, if it is already visited, what I mean by this, let's suppose from 3 the 0 is the neighbor, right, but you can see this 1 is already visited. In that case what we have to do, we simply have to change its low value. So this is the low value. Okay, you can understand this, and this is the capture. Okay, so we basically have to change its low value with the minimum value of both. Okay, so you can see, so we will change the low value of the current node with the minimum value of the neighbor or the current node. So whatever the minimum in these two, we will take this, because we have to make everything every node which is in the cycle as same low value. And let's suppose if it is a new neighbor, so we have to call it again, right? And after calling it, when we come back from the recursion as you see here, when we come back from this, what we do, we basically first convert, basically first change the low of current node, right? Now you can see in that case, if the current node is 0, so if we try to this 0 and this is 1, so the current, this is a current node, okay, its low value is 0, and this one node is the previous node with which we are checking, and its low is 1. Now you can see that its low value is greater than this current node, and if it happens, it means these are not identical, and this is the edge that we can remove and make two components, right? That's what we are doing. If the low of neighbor is basically greater than, so this is the neighbor now, and its low is greater than the low of, or capture we can say, current node, in that case, that current node and neighbor is the edge, which is a critical edge, and we basically append it, and that's how we solve this problem, that's how we go through this problem, and we are easily solve it. So yeah, it is a very interesting one. You can rewatch the video to understand this concept. Other than that, you can simply raise your doubt, I will surely help you. Okay, so thank you, I hope you like this problem. Bye bye.